Hi there everybody and welcome back to my channel. This time I'm going to be taking you through an explanation of the answers to the 2017 Breadth in Chemistry exam paper multiple choice questions, and this is for the OCR-A specification in A-level chemistry. Both a copy of this exam paper and its mark scheme are available on OCR's website, but the multiple choice mark scheme is literally just a series of the correct letters. Hopefully with this explanation of each question's answer, you should have greater insight into why each correct response is as it states in the mark scheme. So, kicking off with question 1, which ion has a different number of electrons from the other 3 ions? So using the proton numbers from the periodic table, so that's the atomic number for each element, and considering the ionic charge on each of these, I've been able to put together this list which represents the number of electrons in each ion. And you can plainly see when I've done this that the gallium 3+ ion has got significantly more electrons than the other 3, giving us our correct answer of A. I would like to make the point though that you'd actually be able to answer this question just off the proton numbers. Because unless that gallium was going to have a ridiculously high positive charge on its ion, it's definitely going to be the gallium that ends up being the odd one out, since it has significantly more protons than the other 3. Moving on to question 2, and you can see we have a fairly standard empirical formula calculation question with a lot of distractors. So my recommendation is do your normal working out as I've done here, and ignore all of these until you are completely satisfied that you've established the simplest whole number ratio between your elements in the formula. And so here, for instance, I've got 2, 5, and 1, which leads me directly to answer D. These distractors, which are very close examples to the correct one and multiples, these are deliberately done to distract you from the correct answer. So my recommendation is do your full working out as normal, treat it like any other question, and then once you've got an answer, then you need to go to the list. Moving on to question 3. Samples of 4 hydrocarbons are completely burnt under the same conditions of temperature and pressure. Which sample produces the greatest volume of CO2? Now, since I'm aware that I'm working under the same conditions of temperature and pressure, I don't need to actually consider volume of CO2, I can consider moles of CO2. So if we reimagine the question as asking which sample produces the greatest moles of CO2, then I'm able to answer this much quicker, and I don't let myself get confused by thinking what calculation for volume am I meant to be using and so on, because we don't have any more data. I'm also going to use the relationship that I'm aware of between a hydrocarbon and CO2 in a combustion reaction equation. The relationship I'm aware of is however many carbons there are in the formula of the hydrocarbon is going to match the balancing, the stoichiometry, in front of the CO2. So for example, in any combustion equation for these, C2H6 is going to give me 2 CO2, C3 is going to give me 3 CO2, C4 for 4, and C5 for 5. And so I'm able to determine that balancing without writing out the full reaction equation, which again would take more time. I can then use this ratio, for example the top one here of 1 to 2, in determining the number of moles of CO2 produced when this hydrocarbon is combusted. So 0.4 mole of ethane, which is the C2H6, is going to produce 0.8 mole of the CO2. And I do this all the way down the list, leading me to my correct answer of B. Question 4. Which reaction produces the smallest atom economy of BaCl2? So I've got a little sketch out here of the atom economy calculation for the BaCl2, and you can see that on my numerator I have just the BaCl2, that barium chloride, and on the denominator I have the BaCl2 and other products. Now if I want to get a nice small atom economy for the BaCl2, I need this other products quantity to be as big as possible. So as you can see, what I've done then is I've gone down the list and I've looked for which option has the largest value with regards to molar mass for all of the other stuff that comes with the BaCl2 in the products. As a result, I've determined that C would have that greatest value, meaning that C is going to give me the smallest atom economy for the BaCl2. Moving on to question 5, the burette readings from a titration are shown below. So we've got 2 separate readings, and that's going to give us a titer of 19.95. The burette used has an uncertainty of plus minus 0.05 centimeters cubed in each reading. Now that's really important, because since 2 readings were used to determine that titer, I'm going to need to incorporate that fact of 2 readings were used into my calculation. What's the percentage uncertainty of the resulting titer? So the traditional calculation for this is going to be the plus minus figure divided by the reading times 100. However, you'll also notice I've got this times 2 in there, and that's because 2 readings were used, so this particular uncertainty was encountered twice, and so I've included that on my numerator. If I perform this calculation, my correct answer is D. Again, you've got some distractors in here, so I'd recommend ignoring them completely and doing the calculation with all your working out shown as normal. Moving on to question 6. Which element has atoms with the greatest number of singly occupied orbitals? So to answer this, what I've done is I've identified which block in the periodic table each of these elements belongs to. So I've got P, P, S, and P. And then I've drawn the respective boxes that represent the outermost subshell for each of those elements. And then, based on how many electrons it has to put into that outermost subshell, I've filled the orbitals up, the boxes, singly at first. So for example, carbon is in the second column of the P block, so I knew I had 2 electrons to put in. Chlorine is in the 5th column of the P block, and so I knew I had 5 electrons to put in there. Calcium is in the 2nd column of the S block, and gallium is in the 1st column of the P block on the periodic table. Not forgetting to fill the orbitals up singly at first, so for example you can see I've done that with the carbon at the top. I've not put them both into the left-hand box over here to begin with, I've put 1 in each box going down the line. That means my correct answer here for the singly occupied orbitals is going to be carbon, because I've got 2 just here. Question 7. Which compound has polar molecules? Here's a tip for you. Look for lone pairs. If you look for lone pairs on the central atom, this is a really good indicator of whether you're going to have a polar molecule or not. Going down the list, you can see that the common feature is we've got lots of chlorines involved all the way through here, so these are all chloride structures. And if we look at the first option up here, OCl2, this is very, very similar to a molecule of H2O, which we know is an example of a polar molecule. As a result, I'm able to determine that A is my correct answer here because that's a polar structure. For B, I would have trigonal planar, which is non-polar. For C, I'd have tetrahedral using the 4 Cl's around the carbon, that's also non-polar. And for the SCl6, I've got octahedral, and that's non-polar as well. Even though these structures would contain polar bonds as well, just like option A would, the dipoles in these would cancel due to the symmetry of the molecules. That doesn't happen for option A since it has a non-linear shape and the dipoles do not cancel. Moving on to question 8. Which element has the highest melting point? This is quite a quick one really, if you've learned from module 3 that these 3 are simple molecular lattice structures and typically have very low melting and boiling points, whereas silicon, much like the carbon allotrope diamond, has got a giant covalent lattice structure which requires breaking strong covalent bonds to melt. So our quick correct answer here is A. Moving on to question 9, we have a similar setup here. This can be answered very quickly if you're very aware of the theory surrounding the halogens group. They are all diatomic molecules in the simple molecular lattice structure, which means we should have some good recall here of London forces, also known as induced dipole-dipole interactions, being the only factor that affects the melting and boiling points down the group in the halogens. So here our correct answer is D. Question 10, which silver compound is insoluble in concentrated ammonia solution? Again, this is a quick recall one. You should be aware that it's silver iodide that's insoluble in concentrated ammonia. AgBr is soluble in concentrated ammonia, as is AgCl, and then just the AgCl from this silver halide selection, just these three here, just the AgCl is soluble in dilute ammonia solution. The AgNO3 is soluble in all concentrations of ammonia, and we're assuming that based on its solubility in water. Moving on to question 11. We've got 50 centimeters cubed of 1 mole per decimeter cubed sodium hydroxide and 50 centimeters cubed of 1 mole per decimeter cubed nitric acid being reacted together in a calorimeter, and the temperature increases by 6 degrees C. The experiment is then repeated, but the volumes of the two solutions are halved, and we're asked what the increase in temperature is for the second experiment. Well, this one has been quite confusing for lots of students historically, because the correct answer is C, it would be the same, with the obvious red herring here being B, the idea of it halving. Because lots of people look at that calculation and think, right, the moles are halving, so therefore there's less reaction taking place, so it must be half as well, and so it's got to be B. But if we actually were to look at the number of moles reacting per unit of volume, since the volume and the mole values both halve, we expect to see the temperature change stay the same. Now, you can actually prove this by working through the data, as for both of these scenarios, the enthalpy of neutralisation would need to come out as the same quantity. So if you do Q equals mc delta T, and then minus Q divided by N, you need to end up with the same value. And the only way to do that, if you have to halve the value of M, and you have to halve the number of moles, is to maintain the same temperature change. Moving on to question 12, we have a Hess diagram question where we're asked to calculate the enthalpy change of the reaction using enthalpy of combustion data. Remember, if Hess has a house, then we burn it down. So since we have combustion data, all of my arrows here point downwards towards the combustion products of everything from my reaction equation. I then put multiples for any that require it onto the numbers. And I remember that my Hess diagram is traditionally going to take me round in a cycle like this, going round from A to B, and at the moment, this arrow is pointing the wrong way. So what I need to do is reverse this arrow round the other way and make the quantity for that particular enthalpy change now a positive value, which I've reflected in my calculation below. All I then need to do is add up the alternative route, and I get my answer, which is B just here. Question 13. The reversible reaction below is allowed to reach equilibrium. Which change in conditions would be expected to shift the position of equilibrium towards the products? And immediately here you can see that I've taken out options A and C. And the reason for that is, this particular equilibrium will not respond to a change in pressure, since it has an equal number of moles on either side. So I'm definitely only looking at B and D, which are temperature changes. Since the forwards reaction is exothermic, I know that if I decrease the temperature, I will shift the position of equilibrium to the right-hand side. So my correct answer here is B. Question 14. What is the systematic name of the compound below? Now, I've redrawn the molecule outside of skeletal formula just here, and I'd recommend, if you're not a brilliant skeletal formula student, I recommend you do the same. And I would also recommend it for anyone when it comes to EZ or cis-trans isomerism, because it is much easier to see the double bond out like so. Here you can see in the list that we're meant to not only determine the longest continuous carbon chain, because we've got butte versus eth, but I also need to determine whether this is the E or the Z isomer. So, first off, I've redrawn the molecule, and you can see in the red numbers going through here, I've counted out my longest continuous carbon chain. That means I can immediately eliminate options C and D from my selection, since they assume that eth is the longest continuous chain, and I can see that it's 4 carbons being butte. Then what I've done is, for my carbons 2 and 3 just here, I've gone to each one at a time, and had a look where its high priority group is, using the Kahn-Ingold Prelog rules of atomic number to assign priority, and that's going to help me determine whether I've got the E or the Z isomer. So I'm drawing out my double bond. I go to carbon number 2 first, and using the blue numbers here, you can see I've considered the bromine and the carbon, identifying with a little bubble around it the bromine as the high priority group for the left-hand carbon. I then go separately to carbon number 3 just here, the other one from the double bond, and I have a look at the atoms immediately bonded to that carbon. I've got a carbon at the top and a hydrogen just here with the blue numbers of 6 and 1, identifying this top group here, so this carbon atom immediately bonded to the carbon on the right as my high priority group. That means if I look at the position of these two high priority groups, I'm able to determine that this is the E stereoisomer, so my answer is A. Question 15. The skeletal formula of an organic compound is shown below. What is the molecular formula of the organic compound? This is just a matter of interpreting skeletal formula. What I've done is over here, and I'd recommend if you struggle with these that you do something similar in the exam, but you could always just label up the structure you already have. I just wanted to give you an alternative one, a bit bigger. I've gone through and I've labeled up all the carbons and hydrogens all the way through so I don't miss out any hydrogens, and my molecular formula works out to be C. But you can see here from the list of distractors, they are very similar to each other, so I'd really recommend taking your time and double checking. Question 16. How many structural isomers have the molecular formula C5H12? This is an alkane, and I can tell that from the formula. And I've had a quick sketch of my different examples just here that I can have for this. There is no quick way to do this. There's no shortcut, there's no special formula. You just have to have experience and practice. So I'd recommend having a go with different kinds of functional group in chemistry, like alkanes, alkenes, and alcohols, for example, about how many different types of structural isomer you can get from a formula that's, say, at least 5 carbons long. Correct answer here is B, and I've given you the 3 structures here. Question 17, which organic compound has the lowest boiling point? Now, a quick bit of deduction would say that all of these structures are C8H18. And so that means all I need to really consider when it comes to boiling point isn't really anything to do with the number of electrons. I am really concentrating on here, as I always should with any response regarding boiling points of organic compounds, I am concentrating on my intermolecular forces and surface area contact points. These are all C8H18, which means I know that London forces are going to be the strongest type of intermolecular force. And the more branched a molecule is, the fewer surface area contact points there are between the structures. That gives you weaker London forces that require less energy to be broken. So the lowest boiling point is going to be this very branched structure, A. Moving on to question 18, we're asked which alcohol reacts with an acid catalyst to form E and Z stereoisomers. This is a real time thief question, and I'm very grateful that the correct answer was A here, because if it was further down the list, you're definitely going to be on this one for quite a while. I've written out the reaction equation for you so you can see the product of pent-2ene here for when the pentan-3ol reacts with an acid catalyst to form an alkene. And I'm also aware that I was meant to be forming an alkene because the question mentioned E and Z stereoisomers, and that only applies to the alkene functional group in organic chemistry at A level. What I'm looking for then is in the products for any of these, it just so worked out to be that A was the correct answer. I'm looking for each carbon in the double bond to be bonded to 2 different atoms or groups either side. So they can be the same as each other. So for example, they could have an X on either side here. That could be 2 Cls, or it could be 2 CH3s, but each carbon needs to be bonded to 2 different substituent groups. That is what happens in the product of pent-2ene down here. It doesn't happen for any of the others. If you'd like to back that up, I recommend you write out the reaction equation for each of these and you'll see what I mean. Question 19, fantastic Spectra question. An alcohol is heated under reflux with sulfuric acid and potassium dichromate 6. The organic compound formed produces the infrared spectrum below. Now, looking at the spectrum straight away, we can see we've got no OH of any kind. So we've got absolutely no carboxylic acid OH group, because that would be a huge peak through here like that. And we've got no OH alcohol group, because that would be a huge shape like this just here. And we've definitely not got either of those two. I do have quite a generic CH peak just here, but I've got the brilliant C double bond O, which indicates normally an aldehyde or a ketone, especially without the presence of the OH group here, which would be for a carboxylic acid, for instance. And it could also represent an ester, but I'm going well outside the realms of the question here, because I've been told the alcohol has been heated with acidified potassium dichromate, which tells me that I've oxidized my alcohol. And the suggestion here, because there's no OH and there's only this C double bond O, is that when heated under reflux, an alcohol which is secondary could perform a reaction to produce a ketone, which would give me exactly this kind of spectrum. So what I'm looking for now in my list below, before I even get to it, you'll notice I've not even addressed the list below. I'm looking for an alcohol which is secondary. A primary alcohol would produce a carboxylic acid when heated under reflux with sulfuric acid and potassium dichromate 6, so I would have had a huge peak over here. And a tertiary alcohol wouldn't actually react, and so I wouldn't have this peak, and I'd have the original OH peak for the alcohol over here on the left-hand side. So I'm definitely looking for a secondary alcohol because that will form a ketone. Going down the list, I can see that option A is tertiary, so can't oxidize. Option B is exactly what I'm looking for, a ketone, and I've written the reaction equation out here for you. And then option C and D are both primary alcohols, which would become the carboxylic acid I mentioned. So my correct answer here is B. Which alcohol is not likely to have a fragment ion at mass to charge ratio 43 in its mass spectrum is our final question 20 in this multiple choice series. Now, a mass to charge ratio of 43 is normally because of one of two different fragments, these. So they are 3 carbon chains, and you've got a positive charge, because obviously a mass to charge ratio and the fact that it is a fragment ion, it needs to have that positive charge. We're looking for 3 carbons together, fully saturated, obviously missing something at the end because we've got this positive charge just here, or you could have this structure where the positive charge is located in the middle. Either way, 43 is a very common structure piece like these in organic chemistry as a fragment. So then I basically go through all of the structures in here and I'm trying to find the molecule that doesn't have this. Now what I can see, even though the correct answer is A, let's give a little bit more information. I can see this kind of a fragment could be possible here from B. I could also see that this kind of fragment could be possible here from C. And I can also see that this kind of fragment could be possible here from D. But there is absolutely no way that I could have this fragment up here in A because of this bonding towards the right-hand side of the structure. So my correct answer here is A. I hope you found going through these multiple choice question answers helpful and it gave you greater insight into the mark scheme. In the video description, I'm going to put links to the paper and mark scheme themselves, and I'm also going to put a copy of my version of this mark scheme so you can download a set for yourself and use it for your revision. Thank you very much for watching, and until next time, happy revising.